My name is Sally Widlund, and today I will be discussing the proton NMR spectra for both ethanol and naproxen. Pardon my voice, I just recently got a cold, so I sound kind of terrible, but we're going to go ahead and start with ethanol. So as you can see from the structure here, ethanol is a relatively simple compound, which consists of a methyl group over here, so CH3, which is bound to a hydroxy group, which is just characterized by that oxygen bonded to hydrogen. The carbon of the methyl group is sp3 hybridized, as is the carbon of the methylene group. The three hydrogens which make up the methyl group can all be considered chemically equivalent, as they all exist in the same chemical environment. In other words, all three hydrogens are bonded in the same way to the same sp3 hybridized carbon and will therefore be expressed as one signal on the proton NMR spectrum for ethanol. The two hydrogens bonded to the second sp3 carbon are chemically equivalent to each other, as they are bonded to the same atom and are equally distant from the hydroxy group in comparison with one another. So I'm just going to take a minute to go ahead and draw in those implicit hydrogens, just so we get a better idea of what we're talking about here. So right here is the carbon, and then this will be a bad drawing, but three hydrogens coming off there. And those three are equivalent. And then two hydrogens here, equivalent. All right. So the hydrogens connected to the second sp3 hybridized carbon are significantly closer to the hydroxy group than the hydrogens of the first carbon. This means that those two groups of hydrogens are not chemically equivalent. Therefore, the hydrogens of the second carbon will appear as a separate signal from the hydrogens of the first carbon. So far, we have two distinct signals that will show up on the NMR spectrum. So our final hydrogen is connected here to the oxygen, which makes up the hydroxy group or the alcohol group. This oxygen is a much more electronegative molecule than anything else in this compound, which means it has the tendency to pull electrons towards it, and therefore it has an effect on the hydrogens in the molecule. So the hydrogen connected to the oxygen will be it'll have a much different chemical environment than any of the other hydrogens in the compound. So this hydrogen over here will appear as its own separate signal on the NMR spectrum. So now that we've established that there are three signals present in the proton NMR spectrum of ethanol, we're going to go ahead and go into further detail about each respective signal. We'll start by discussing the location of each signal. So as you can see over here, we're looking at, sorry, I'm just going to zoom in a little bit, but here's the NMR spectrum, the proton NMR spectrum for ethanol. So as you can see, here's signal number 1, 2, and 3, and we'll discuss what each of those smaller lines mean as we get a little farther into this. But to start out, we'll start just by describing kind of the scale here. So ppm is just the measurement used, or the scale or the units used in NMR. And so the location of an NMR signal indicates where a particular proton or group of chemically equivalent protons absorbs based on its chemical environment. Changes in locations of signals are known as chemical shifts. Chemical shifts are influenced by electron density, the electronegativities of neighboring functional groups, and diamagnetic anisotropy, although this particular factor is specific to aromatic protons. The electronegativity of neighboring groups is particularly important as electronegative atoms have a tendency to pull the electron density of the compound in their own direction and cause protons to be exposed to greater amounts of radiation. This causes them to absorb at higher frequencies, which shifts the NMR signal downfield. So when we say downfield, we mean further away from zero, which sometimes seems a little counterintuitive as the numbers are getting bigger, but upfield is closer to zero, downfield is farther from zero. So a shift downfield, again, is a shift away from zero and towards higher ppm. A shift upfield is towards zero and towards lower ppm. And as I mentioned briefly, ppm is the unit of frequency at which a proton absorbs radiation and stands for parts per million, which is just kind of a general unit used many different times in science. The most electronegative atom in ethanol is oxygen. This means that the signal associated with the hydrogen, so again, that's this hydrogen, but the hydrogen bonded directly to oxygen experiences, it will experience the greatest downfield shift, again, towards the higher numbers. This is because that particular hydrogen experiences the most de-shielding by the oxygen atom due to its proximity to the oxygen atom. The next closest protons to oxygen are the hydrogens on the methylene group. So these two hydrogens right here. The signal for these protons will appear farther downfield than it otherwise would, but not quite as far as the signal for the hydrogen directly on the oxygen atom. And as we said before, those are two separate signals, so it makes sense that they would be in two separate ranges. Finally, so that again, that would be this signal right here for these two hydrogens. And then finally, the signal for the hydrogens of the methyl group will be farthest upfield, as there are more than two bonds between them and the oxygen. So we would count that as one bond, two bonds, and then each of the bonds to the hydrogens would count as another bond. So now that we have a general idea of where we can expect to see each signal, let's take a look at the actual proton NMR spectrum of ethanol as we are here, and analyze the numbers themselves specifically. So looking at the spectrum, it's easy to visualize those three separate signals. But we'll go ahead and start with the peak furthest downfield because that's kind of the simplest one we have in this spectrum. So this signal right here represents the hydrogen atom bonded directly to oxygen. So literature values state that protons, which are part of hydroxy or alcohol groups, can be found anywhere from 0.5 to 5 ppm. Most commonly, these signals appear between 3.5 and 5 ppm, but in the spectrum of alcohol or of ethanol, the signal for alcohol can be found at approximately 3.7 ppm. So this spectrum we're looking at right here is kind of an estimation created by ChemDraw, but it's easier to zoom in. So this isn't entirely accurate, but it gives a better idea of splitting patterns than other literature ones do. So take this with a little bit of a grain of salt. So alkane type protons typically, okay, so the next thing that we need to talk about now that we've established where on this spectrum each of those signals is going to appear, next we need to discuss the integration of these different signals. Or the area underneath the signal. So ethanol is kind of a bad example of this, but in certain compounds, you can have, well, I guess it's a decent example because we have 6 hydrogen atoms in this molecule. And so therefore, we would kind of expect to see 6 different signals, one for each hydrogen atom. However, we only see 3, and that's because of the chemical equivalence of these different hydrogens. So as you can see, the different signals in the spectrum of ethanol are broken up into different little peaks there. And that is due to a phenomenon called spin-spin coupling. And so spin-spin coupling is basically a concept that describes the magnetic interactions between neighboring but non-equivalent nuclei which are active in NMR. So just to rephrase that a little bit, a signal won't split if there's only one proton, so like this signal, for example, and the two protons cannot be exactly equivalent. And different patterns occur for different reasons. So this right here is what we would call a triplet, because as you can see, there's one taller peak and two basically equivalent smaller peaks. And so that is because, so the spin-spin coupling basically describes what's going on the neighboring carbon. So this signal here, and there's a formula that goes along with it. So to predict the number of peaks or splits, you can use the equation +1. So where N is equal to the hydrogens on the neighboring hydrogen. And so this type of splitting is simply known as first order coupling because it involves like the direct interaction between two hydrogens. So basically, so for this hydrogen right here, we have two hydrogens on the neighboring carbon. So this would be 2 + 1 = 3 signals. So that's why we see 3 signals here at like approximately 1.2 ppm. And then if we look at this carbon, we count the carbons on, or the hydrogens attached to the carbons or to the atoms on each side of it. So we have 3 hydrogens here, 1 hydrogen here. So we have 4 for N plus 1 is 5. No, I'm sorry. So we don't include, it's only the carbon next to it. So we don't include the oxygen. So here it would just be 3 + 1 = 4. And that's why we see those 4 signals there. And then finally, on this last hydrogen here, there are no hydrogens on oxygen other than that one hydrogen in question. So therefore, this would just be 0 for N plus 1 = 1. The last thing we need to talk about, and I just messed up my diagram here. But the last thing we need to discuss for this particular spectrum is the integration of each signal. So simply put, the integration or the area under the signal is a useful tool to determine how many hydrogens each symbol or signal represents. So let's see, I don't think it'll show on this particular spectrum, but we can kind of infer. So basically the integration will tell you how many hydrogens each signal represents. So since we already talked about the splitting, we can like assign each signal to each part of the hydrogen. So this one here, farthest downfield, would represent the hydrogen attached to the oxygen. So clearly it just represents one hydrogen. This guy here, the quartet, would represent the hydrogens coming off of this carbon. So it would have an integration of 2 because it represents 2 hydrogens. And finally, the signal at 1.2, which represents the methyl group, would have an integration of 3 because it represents 3 hydrogens. So those are all the components of this particular spectrum. Nothing too crazy, nothing too complicated. So we'll go ahead and make it a little bit more challenging and move on to both a more complicated compound and a more complicated spectrum. So just give me a second here to erase, and then we'll go right ahead to a compound called naproxen. Okay, so naproxen is in the class of NSAIDs, which are non-steroidal anti-inflammatory drugs. So it's kind of similar to ibuprofen in that sense, but as we can see, it's much more complicated than ethanol. It has a benzene ring right here, so an aromatic compound. It has a second cyclic structure. Over here we have an ether and then a carboxylic acid on the end. So it's important to identify those structural groups so you can kind of know the ranges that you should be looking for on the scale or on the spectrum. So to begin, we can go ahead and identify that the most electronegative atom in this compound is oxygen, and oxygen appears 3 times. And then let's go ahead and draw in the implicit hydrogens in this compound. To begin with the easy hydrogens, we have 1 here, and then we'll know that this is a methyl group, so we'll have 3 here. Nothing on this oxygen, just those 2 lone pairs. Here we have 1, 2, 3, 4 bonds, so no room for a hydrogen. Here we'd have 1. Here we'd have 1. Again, 1 here. Here we have those 1, 2, 3, 4 bonds, so no room there either. But another one here, 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 and then this also represents a methyl group. So we'd have 3 coming off here. And then from this particular carbon, we would have another implicit hydrogen down here. And that takes care of our whole molecule. So we have 3, 6, 9, 12, 13, 14 hydrogens in total. And now it's time to determine the number of signals we should have. So I've gone ahead and circled the different groups that are going to appear as different signals on our NMR spectrum of naproxen. So let's just discuss why each of these would appear as a different signal. So go ahead and look at where those specific groups or signals of hydrogen or of protons will show up on the spectrum of naproxen. So starting down here at approximately 12.5 to 12.7, we can see this singlet, which can only represent this particular hydrogen connected to the oxygen on that hydroxy group, which is part of the carboxylic acid that we see right here. So that's going to be farthest downfield because the hydrogen is connected directly to that electronegative atom. We move in here between about 7 and 8 ppm and things start to get a little bit messy. So as I mentioned, each of these signals on these cyclic hydrogens here, or of the hydrogens on these cyclic compounds, is going to appear separately, but they're all relatively close together. So we can go ahead and zoom in just a little bit, maybe not that much, and we'll see that there are some interesting splitting patterns going on here. So, sorry, zoom. You can see we have some doublets going on. And like we mentioned in ethanol, the splitting patterns are determined by the numbers of neighboring hydrogens. So if we go ahead and take a look here, we have basically, this is kind of a doublet of doublets. Here's another doublet and another doublet. So the region that would make most sense for this is these hydrogens here. So for this one, it would only have one neighboring hydrogen, so it would be a doublet. for both of these two. And then for this hydrogen, it has no neighboring hydrogen, so it would appear as a singlet. And that would also be the case for this particular hydrogen here. On both of these two, we would have another doublet situation. So that explains kind of the complexity that we're seeing in here. It's just because we have some interesting configurations of hydrogens going on out there. So more specifically, the signal for this hydrogen would appear at approximately 7.23 ppm. This one would appear at 7.78 ppm. Right here we have 7.34, 7.06, 7.73, and 7.48. So you can see that they're all right in that range. They are in the correct range for an aromatic compound. So that's why you might be thinking, I thought, alkenes were further down in the scale, but since those are part of an aromatic compound, that benzene ring, they would be further down in that 6 to 8 ppm range. So then we'll go on upfield a little bit. Ooh. And that is one big peak there. So we can see we have some more. That would actually be, so 1, 2, 3, 4, 5. That would be a kind of an interesting signal to interpret there, but it makes some sense because we have, so it would be for this hydrogen right here, because we have 3 here, and then sometimes those signals just get a little funky in there. So that's why we would see such an interesting splitting pattern there. And then furthest downfield would be the hydrogens of this methyl group, which show up as a doublet because their neighbor is this single hydrogen here. So that kind of gives you an idea of why each of those particular signals shows up where it does. And then the last thing we have to talk about is the integration. So starting down here at the 12.72 ppm, it's a singlet, but we also just know that it represents that one hydrogen. So that's kind of an easier one. Each of these signals in that messy region would just represent one individual hydrogen because we know that those are all part of that cyclic compound. This really tall peak right here is actually, I made a mistake before, but it's actually going to be a combination of 2 similar signals. So it won't really let me zoom here, but there we go. That would actually represent each of these methyl groups. And so that's why, so it's 2 separate signals, because we have the quartet here. And then, so that would represent this, the hydrogens of this methyl group. No, it would represent this hydrogen, and the quartet forms because of the hydrogens of this methyl group. So because the neighboring hydrogens to this single hydrogen are 3, we would have 3 plus 1 equals 4. So that's why you're seeing that quartet splitting pattern. But then over here, these hydrogens show up as one signal. So that's why you're seeing that one really big, tall signal. And they'd show up as a singlet because there are no hydrogens on that neighboring oxygen. So this signal itself would represent 3 hydrogens. This would represent 1. And then down here, we have the doublet that would represent these 3 hydrogens. And that should explain everything.